Good morning, dear all. We will start the new lectures, and we will continue the theme of previous lecture. And I'm going to discuss the following basic notion, such that linear systems, determinants, matrices, and I'll try explain in the second half what mean cross product. What mean cross product? I recall some definition which was done in the previous lecture. What mean linear system? Linear system and or equivalent the system of linear equation is a system of the following kind. The linear equation, the equation of the following kind. The equation which contains the unknown in the first degree and the linear combination of such unknown, and we have some various linear equation, and such system of equation is called linear system of equation. The solution of such system is an n-tuple of the numbers you can consider such n-tuples as some vector in the arithmetical vector space Rn, and we also can interpret this system as some each equation we can interpret it as the equation of of some hyperplane in the n space, and solution is the intersection of such plane. The solution is some points, and the solution means that if we substitute some values in the linear equation, we obtain some equality. The equality for the every linear equation, namely and so on. For example, if we have only one equation, for example, let's we have the following simple linear equation which contains only one equation, and this equation has only two unknowns, x1 and x2. What means the solution? We can consider, for example, the two-tuple 1, 0, and if we substitute this tuple in the equation, we obtain equality, and this pair of numbers is solution of this equation. We also can consider other tuple 0, 1, and if we substitute these values in the this equation, we also obtain equality. We have two solutions of this equation, but we can note that if we substitute some other tuple, for example, the ratio 1, 2, 1, 2, 1, 3, 2, 3, and so on, we also obtain the equalities. And easy to see that this solution has the infinitely many solutions. And if we draw coordinate system in the plane, and if we will mark the points which has the coordinates which are which are and two tuples which corresponds to the solution of this equation. For example, one, this point has coordinate 1, 0, and this point has coordinate 0, 1, and this point, this coordinate ratio 1, 2, 1, 2, and so on. We obtain the sum straight line, and every point of this straight line corresponds to the solution of this equation. And we can write this solution in the following form. We can express one of the unknown using other, and we can present the whole solution in the form of this on this expression. x1 is equal 1 minus x2, and we can substitute in x2 the arbitrary values, arbitrary real numbers. Let's introduce the parameter, maybe t, and let x2 is equal t, and x1 is equal 1 minus t, and we obtain the some expression for all solutions of our equation in this following form. And we consider this expression as some formula or maybe some function which expressed the points which are corresponds to the solution, to the solutions of our equation in this following form, which expressed these values from values of some free parameter t. And all we have in this case infinitely many solutions which can be present as the points of some straight line in the plane. In this case, we have infinitely many solutions. And the following example. The following example. Example 1. Example 2. Let's consider also other equation. We have two equations. First of all, x1 plus x2 is equal 0, and other x1 minus maybe 3. X1 minus x2 is equal 1. And in this case, we also can express from the second equation the first unknown x1 as the x2 plus 1. And we can substitute this expression in the first equation. After then, we obtain the equality x1 plus we substitute x1 and we obtain x2 plus 1 plus x2 is equal 3, and 2 times x2 is equal 2, and x2 is equal 1, and we can express x1 as x1 is equal 1 plus 1 and is equal 2, and we obtain the solution of this equation, and the solution is equal x1 is equal 2, x2 is equal 1. And in this case, we have only one solution. We also can present this solution using geometrical presentation of this equation. Using previous example, we can present the first equation as a straight line in the plane. The all solution of this equation are the points in the plane, and we can find two solutions. For example, for example, 3, 0, and the first solution of this equation, and the point on the coordinate line 0x corresponds to the solution, and this point has coordinates 3, 0. Let's note this point by A, and the second point 0, 3, the first solution of this equation. As we noted, as we can see the first example, the all solution of this equation are from the straight lines which meet these 2 points A and B. And the straight line presents the all solution on the first equation in the following sense: every point of this straight line corresponds some solution of this equation, and we have infinitely many solutions of the first equation. By the same way, we can obtain a description of all solutions of the second equation. And let's try to glass two solutions of this equation. And also we can express the first unknown of the second solution, x1, as the sum x2 plus 1, and we can consider every values of the second unknown. For example, maybe x2 is equal 0 and x1 is equal 1. Maybe other values, maybe x2 minus 1 and then x1 is equal, oh, I'm sorry, yes, it's true, this point C, which has coordinates 0, its coordinates 1, 0, and other point x2 minus 1 and the second, x2 is minus 1, x2 is minus 1, and zero. x1 is 0. This point. Maybe x1 0 minus 1. And we obtain two straight line, and intersection point of this line M0. This point belongs to the set of solution of the first equation, and this point belongs to the solution of the second equation. And this point of intersection of this straight line is a solution of this linear system. Easy to see that this point M0 has coordinates 2, 1. And if we substitute these values in the equations of our linear system, we obtain the two equality. And we can see that in this case we obtain a unique solution of this equation. Unique solution. And this solution is a point of intersection of straight line which presents the solutions of this linear equation. And we can generalize this to example, and we can consider arbitrary linear system of two linear equations with two unknown, and let this equation will be A11 in this following form, this equation A11 and A12 is arbitrary real numbers, and two linear equation with coefficients A21, A22. And we can rewrite this linear system in the form so-called matrix. This matrix, which contains the following entires: the coefficients of linear system and the numbers which lies in the right side of all of our equation. Maybe we will call these numbers free terms of our system. And easy to see that we can express the solution of this equation in this following form. In the following way, let's multiply the second equation by A22 and multiply the second equation onto A12, and let's substitute from maybe this. This coefficients is considered the coefficients, the second coefficients of the second equation, and these coefficients considered these coefficients of this equation. After multiplication, we obtain the equals coefficients for two equations, and after subtraction from first equation, second, we kill the coefficient of second unknowns, and we kill the second unknowns, and coefficients for first unknown after some subtraction is equal this expression. Oh, I'm sorry, this expression. This expression, namely the product A11, A22 minus A12, A21. And the free term will be equal the following product: B1, A22 minus A12, B2. And we can express the value of first unknown as a ratio of this expression, but only in the case when denominator is not zero, is not equal 0. And by the same way, we can obtain the expression for the second unknown, x2, in the same form. We can see that both expression denominators are coincide, and we can introduce the special notation for this expression. Let's delta is the values of denominator in this form. And we will denote by delta 1 the expression for the x1, namely delta 1 is equal b1 a22 minus a12 b2, and let's delta 2 is equal a1 b2 minus b1 a21. We also can see that the expression for delta can be obtained using the following procedure. Let's consider the matrix with entire A11, A12, A21, A22. And we can see that this product is a product of the diagonal elements. And the second product is a product of the element on other diagonal. And we obtain some procedure for obtaining this expression. Namely, we multiply the elements of the main diagonal and subtract from this product the product of element which lies on other diagonal. And this procedure uses some operation for element of the following matrix. Namely, this expression is defined the following operation. Which corresponds to the matrix, the following expression. And this operation is called determinant. And we'll denote this expression by delta. And easy to see, the expression for delta 1 is the same, can be obtained using the same way. Namely, we can consider the same operation delta by we change the expression for matrix which contains only entire of the coefficients of our linear system by the following expression. Let's change the first column of this matrix onto the column of three terms. And we obtain the following matrix. And our operation corresponds to this matrix the following expression B1A22 minus B2A12. Namely, this expression delta 1. And this operation, if we apply this operation to the matrix which is obtained from the matrix of coefficient of our system by changing two columns onto columns of real terms, and after this changing we obtain the matrix the following matrix, and our operation corresponds to this matrix, the expression A11 B2 minus B1 A21. This expression we called before delta 2, and the theorem Cramer rule asserts that values of unknown of our system can be expressed in the following simple form. x1 is equal the ratio delta 1 delta, and x2 is equal the ratio delta 2 delta. But only in the case when delta is not equal 0. Is not equal 0. This is the main assertion of the theorem which is called Cramer rule. But the determinant delta can be equal 0 if delta is equal 0. Let's consider this case. What means that the delta is equal 0? This expression. Let's rewrite this expression. What means that this expression is equal 0? Easy to see. That means that ratio these terms and these terms are equal, namely the ratio A11, A21, and A21 to A22 is equal. What means? What means that this equality? Easy to see that this straight line, which defined by these formulas, this first straight line, and the second straight line are parallel. In this case, this straight line are parallel. And easy to see that if we have two parallel straight lines, this parallel line hasn't point of intersection. If these two parallel lines are not coincide. But in the case when two straight lines are coincide, the straight line has infinitely many points of intersection. And we obtain the theorem Cramer rule in the following form. We can continue formulate this theorem and write the following two items on this theorem, namely point item 2 of this theorem. If delta is equal 0, we have if either delta 1 is not equal 0 or delta 2 is not equal 0, then linear system has no solution. And this item corresponds to this case, to this the following geometrical situation when the straight line, which corresponds to the solution of the equation of linear system, are parallel. And item B if delta is equal delta 1, delta 2 is equal 0, then our system has infinitely many solutions. Then linear system has infinitely many solutions. And in this case, the straight line which corresponds to the solutions of our linear equation, our linear equations are coincide. We also to generalize this theorem on the case of arbitrary linear system, on the arbitrary linear system with square matrix. But before this generalization, let's consider this operation, the determinant, and maybe we can grasp the simple way to generalize this construction. What means this expression? let's consider the property of this correspondence, and maybe such considerations of these properties can be gives to us the simple way to generalize this construction. So we have the following correspondence. We have some matrix, and we correspond to this matrix the following expression. And this correspondence we call determinant. This correspondence easy to see that this correspondence defined on the we can consider this correspondence as some functions which defined on the rows on maybe columns on this matrix. Later we see that we can consider this correspondence as the functions on rows and the functions on the columns, and the same way to define this correspondence. Let's define the functions on columns. Column of the matrix can be present as vectors, and the same way the row also can be considered as the vector in the two-dimensional vector space. And these vectors and these vectors. Easy to see if we have the simplest case when the first vectors is vector with coordinates 1, 2, and the second the vectors with coordinates 1, 0. The first 1, 0 and the second 0, 1. And in this case, our correspondence delta correspond this pair of vectors the number which is equal 1. Let's try consider this 0 as an area of this rectangle, and if we multiply one of this vector by the some numbers lambda, for example, in this case the area of this rectangles also multiplied by this number lambda. and if we multiply the other row on mu, we obtain the product lambda and mu. The area multiplied by the product of these numbers. Okay, if we add to the second vector first and we obtain the sum, maybe this vector A and this B, and consider the sum A plus B plus A. The area of this figure will be the same. This figure is parallelogram, and the area of parallelogram is product of the base of parallelogram and height, altitude of this parallelogram. And this product is the equal for the product original sides, the sides of original rectangle. And we obtain the two following property of our correspondence, which called determinant. The determinant is a function which defined on the some vectors or rows of the matrix. Let's introduce the following notation. Let's A1 is vectors with the rows A1, 1, A1, 2, and A2, the rows A2, 1, A2, 2. And determinant is a function which defined on the rows. Let's determinant. Determinant is a function A1, A2. And this function which defined by the following formulas. And this correspondence has the following property. Namely, following property. This function is a linear function. What means linear? If I consider the sum of some rows, what mean sum of rows? I mean the sum of rows as the sum of the vectors in the plane. If first rows and the second has entires A21, A22, the sum A1 plus A2, the sum of corresponding entires of these rows, namely the first the first coordinate of this vector is the sum corresponding coordinate. And in the linearity means the following equality determinant from the sum A1 and A2 and A3 is equal to the sum determinant A1 A3 plus determinant A2 A3. Easy to see that this property is true. The direct calculation would mean the left side. If you substitute in this formula, we can change this expression by this, and let's consider A11 plus A21, A12 plus A22, and in this, no, let's the second rows in the definition of our determinant, we will note by B and B1, B2, and after the simple calculation we obtain the following expression. And easy to see, this expression is a sum. The sum of the following expression for which equal this expression for determinant, namely this expression is this first determinant, and this expression is the second determinant. And we checked this equality. We have the first property, such first property of determinant. The second property is very simple. If we multiply by lambda one of the rows, we obtain the product of this scalar on value of determinant. Easy to see, if we multiply one of the sides of parallelogram by some scalar lambda, the area also multiplied by this lambda. And third property is not trivial. The property which asserts that our expression is antisymmetric. If I permutate the rows in the expression for determinant. The right side of this expression, change the signs. Change the signs. And we obtain that the determinant is antisymmetric function. And the last property asserts that the value of the rows 1, 0, 0, 1 is equal 1. The nice thing that this property defines determinant by a unique way. And let's deduce the formula from this property. Let's we have the arbitrary matrix. We also to use the following notation. Let's introduce the notation for the matrix with a straight bracket, and let's this notation will denote the determinant of the matrix. And let's deduce the formula for determinant in this form as a corollary of this property. Namely, the mistake, this one, this one, yes? Yes. I'm sorry. Thank you. Okay. And this one. Thank you. That's my mistake. Okay. I'll try to deduce this formula from this properties, from these properties. Okay, let's suggest that the expression for our determinant is defined only these properties, and we don't know this formula. Let's obtain this formula using this property. Let's suggest that A11 is not equal 0. If A11 is equal 0, we can change the two rows. And after this permutation, the determinant by third property change sign. And we pass to the case when this term is not equal to 0. After them, let's let's consider that from this property easy to obtain the next property if the corollaries of this property. If we to add to the one of the rows of the determinant other, which multiplied to arbitrary scalar lambda, the determinant is not changed. Using the first property, we obtain the following equality: determinant A1, A2 plus determinant lambda 2, A2. And the second determinant we can rewrite in this following form. And we obtain the determinant which the equal rows. This determinant of the permutation of these rows change the signs, but from other side the expression is not changed, and it means that this determinant is equal to 0, and we obtain the equality, the property. If we add to some of the rows other rows which multiply by arbitrary scalar lambda, the value of determinant is not changed. And we will use this property and rewrite our expression in the following form. We can to add to the second row the first row which multiply on the ratio A to 2 and A1 from minus this expression minus for this expression. I'm sorry. A1, and after this addition, we obtain that this term is equal 0. I add to the expression A to 1 the expression minus I to 1, and after this addition I obtain 0, and to A to 2 I add the product of these two expressions. Easy to see that we obtain and this expression I can rewrite in this form. Okay. One more step, and we rewrite this expression in this following form. I'm sorry. Maybe in the first following form. I can to subtract from the first row the second, which multiplied by A1, 2, and I obtain the following expression. And easy to see that this expression kill one other, and we obtain the expression for determinant. And after that we can summarize that the following two assertions. If we define determinant by this formula, the determinant has the following four properties. And other side, if some function has the following properties, this function is defined the following formula. There's some explanation this formula. This formula is uniquely defined by the following properties. And the following property is equivalent, the property of area of parallelogram, but we consider this area with sign. This area can change the sign, is not positive area. The sign defined by order of the rows. And we later will discuss in detail this property changing of sign. But this property can help us to define this define the determinant for the 3 times 3 matrix. We can also to introduce the determinant for the matrix, the size 3 as a sum function which defined by these properties. In this case, we also repeat our previous reasoning and obtain the exact formula for the determinant, which expressed the determinant of the such matrix in the terms of the integers of this matrix. And we obtain the following exact formula, which has enough complex form. Let's introduce the following determinant. We will be noted this determinant by the following symbols. M1, 1, which determinant is called minor. What means minor? Let's consider arbitrary entire of the matrix. For example, A to 1. And let's let's kill rows and column, which defined that this element is intersection of this rows and this column. We obtain some matrix of the less size, namely the size 2, 2, and determinant of this matrix is called minor. Of this element. In our case, M11, we obtain this determinant A22, A23, A32, A33. The determinant M11. M21, this determinant. A12, A13, A32, A33. And M21 is equal A12, A13, A32, A33. And M13. I need only the minors for one of the rows or one of the column. And let's consider the first row. Oh, I'm sorry. I'm sorry. Maybe for first column. First column. And we define the determinant of the three matrix by the sum of product of element of the first column by the its corresponding minors. But before the second summand, we change the signs. Let's consider the minor V signs by this following formula. And general definition of the determinant is the sum of product of the element of arbitrary row or arbitrary column on the corresponding minors V signs. In our case, we can to define the determinant by the other formula. I can consider the element of the first row A1 1 and the theorem asserts that these two definitions are equivalent. Okay. And in this case, in the case of the matrix of size 3 by 3, we also have the same theorem, the Cramer rule, but in this new theorem, determinant is defined by this formula, and system has unique solution, but the third unknown is defined by the formula as a ratio delta 3 to delta. Moreover, we have also the formula, the same formula for the arbitrary square system of linear equation, and in this general theorem the all unknown x1, x2, and xn is defined by the same formula, delta 1 delta, delta 2 delta, and delta n delta, if delta is not equal 0. I don't discuss the item 2 and 3 in this case. We will later, in detail, we'll discuss this general form of Cramer rule. But now I haven't time. 2 minutes, 6 minutes. Oh. I'm going to discuss the important geometrical notion of the cross product, which closely connect with definition of determinant. What mean cross product? I begin to discuss this notion, and we will continue on the next lecture. So, cross product. Cross product. Let's define this product for the two vectors. We will suggest that in the space we choose the standard base I, J, K. The three vectors are form the orthogonal basis, and the length of each vectors is equal 1, the unit vectors. Unique vectors which orthogonal one to other. And let's suggest that if we see from the end of the third vector the shortest motion from the first vectors to second, opposite to motion to our rows in this shortest way. This we can see that in our case the triple IJK is a right triple. But if we change two vectors, for example J, I, K, and if we see from the end of this vector the shortest way to the motion of the first vectors to second, in this case this vector is first and this is second, and shortest way is coincide the way of our row, and in this case we obtain the left triple and this right triple. We will suggest that we choose the basis as a right orthogonal basis, and let in this base the vector u has the coordinate u1, u2, and u3, and vector v has the coordinate v1, v2, v3. And we define the cross product in the coordinate of this vector is as the following formal determinant, which defined by the following formula. What means this formula? We can see that this expression defines defines the sum vectors with coordinates. The first coordinates, these minors. The second coordinates, these minors. And third coordinates, these minors. We obtain the correspondence, the sum expression which corresponds to pair vector, the second vector. And easy to see, if multiply the vector A and G, we obtain in this case vector K. If we multiply A and K, we obtain minus G. And if we multiply J, K, we obtain I. This expression explains the geometrical sense of this expression. I later try to explain the geometrical definition of this cross product. But in this example, give to us some preliminary explanation of this expression. The cross product is the same vector which orthogonal to the plane in which lies the vector which multiplied by cross product. And the length of this vector expressed as a product of the length of multiplied vectors and the area of parallelogram. The area of parallelogram and length of summand is equal. So some preliminary explanation of this cross product. Excuse me, my time is out and I am finished.